All right, so let's go ahead and do our concept review of momentum. So recall that momentum is a vector and it's equal to an object's mass times the object's velocity. And the direction of its momentum is going to be the same as the direction as its velocity. And what it really describes is an object's tendency to keep moving the way that it's moving already. So the more momentum something has, the harder it's going to be to bring it to a stop or make it start moving in a totally different direction. Now, the reason this is useful, one of the reasons, is that momentum is conserved whenever we have a closed system. And this is true even if mechanical energy is not conserved. So in an inelastic collision, for example, there's a loss of mechanical energy, but that doesn't mean that momentum will not be conserved. And what this means is we can usually set up an equation that looks like this for a system, that the total initial momentum of that system will equal the total final momentum of that system. And that equation would look something like this, with one term for each object on the left side and one term for each object on the right side. And these should really all be vectors. So typically you'll need to decide which direction is positive or negative, and then make sure that your velocities have the right sign to represent their directions. And we usually use this during collisions. And in collisions, we're typically going to be able to ignore any external forces because they would be acting over such short times. Now, two types of collisions we studied: elastic collisions. In elastic collisions, kinetic energy is going to be conserved, which means that the initial kinetic energy of the system right before the collision will equal the final kinetic energy of the system right after the collision. And in elastic collisions, objects always bounce. So this would be objects are not sticking together, they're bouncing. Not every time objects bounce will there be a totally elastic collision, right? Objects don't have to stick together to be inelastic. But if the total kinetic energy is conserved, we can call that a purely elastic collision or a completely elastic collision. In an inelastic collision, we have a loss of system's kinetic energy. And anytime an object sticks together, anytime two objects stick together during a collision, this will happen, and it will be an inelastic collision. Impulse. So recall that forces on objects cause the momentum of an object to change. So to calculate the total impulse on an object, you would take the total force acting on that object and multiply by the time over which it acts, and that would equal the change in momentum of the object. Notice this isn't the total momentum, this is the change. So this is the final momentum minus the initial momentum of that object. And those would be the initial and final momentum at the beginning and end of this time interval. We can also find impulse using areas under graphs. So if you have a force versus time graph, and let's say this is the net force acting on the object, if you take the area underneath that force time graph, it gives you the impulse, which is the change in momentum of that object. Also notice that it can be negative, right? So if the area is negative, then the impulse would be negative during that portion. If it's positive, the impulse would be positive during this portion. And remember, this all depends on which way you decided to call positive or negative, right? Because the force will be negative if you were to reverse the axes, for example, for this situation, the graph would change and the sign of the force would be different, signs of the momentum would be different. But just remember that the sign tells you which way that force is acting and which way that momentum is changing in. We also talked about center of mass during this unit. Here's the equation for the center of mass of a system of point masses. Right? It's basically just each object's mass times its distance from some arbitrary position. We sum those, and then we divide by the total mass of the system. So it's kind of a weighted average of positions. Now, the reason that this is relevant to momentum is because by studying the center of mass motion of a system, well, we can understand, we can relate it back to momentum. And sometimes it's actually we can take a really complicated system and simplify it by just looking at the motion of its center of mass. So a couple principles that have to do with this is that the center of mass of a system will have a constant velocity if the net force on that system is 0. Why does my 0 have a little thingy? 0. Right? And this is actually Newton's first law. but it's Newton's first law applied to a whole system instead of just a single object, right? The system will keep a constant velocity if the net force on it is 0. We can also rewrite the impulse equation, but we can do it for systems, right? So if we take the whole net force on a system and multiply by the time over which it acts, we can find the change in momentum of that system. So this works for objects and it works for systems. Similarly, Newton's second law will also work for systems, right? So if we find the net force on a system, it will equal the mass of the system times the acceleration of that system. And I think that's about it for momentum.